If we take a familiar physical object, like a clock tower, and place it onto a standard two-dimensional grid space, we get a baseline for its structure. Every pixel maps to an x and y coordinate. A matrix serves as a set of mechanical instructions that move the space. When applied, we tell every point on this grid to follow a specific rule of motion. This interface shows matrix B stretching the grid and skewing the clock tower. Look at the horizontal and vertical axes pulled off their original gray pathways. The x and y variables no longer act independently. They are mixed together. This mixing process looks chaotic. When every coordinate moves relative to every other coordinate, predicting the final state of the system becomes a massive challenge, requiring us to track a tangle of interconnected variables. If you draw a standard vector arrow anywhere on that grid before the transformation, the matrix will likely change both its length and its direction. Tracking these shifting variables is a dead end for understanding the core rules of the system. It is difficult to find logic when the very markers we use are being knocked off course. To find the solution, we have to look past the components that break and search the mathematical chaos for lines that refuse to turn. Isolating these unchanging lines is the absolute only way to reverse engineer a complex transformation back into its simplest rules. Let's reset the grid to run a test on a single coordinate. We isolate a vector pointing diagonally to the tower's roof at coordinate 2, 2. Running the transformation again, the space skews. But this arrow perfectly maintains its diagonal path, stretching outward to coordinate 6, 6. It never turns away from its line. This is an eigenvector. The prefix eigen comes from German, meaning own or characteristic. This vector represents the matrice's own natural direction. There is one requirement. An eigenvector cannot be the zero vector. Because the zero vector stays at the origin regardless of the transformation, it doesn't provide any information about the matrice's unique direction. These vectors represent the natural, structural input settings for this specific mathematical machine. This graph isolates green eigenvector v1 and its eigenvalue, the scaling factor. Extending to 6, 6, its eigenvalue is 3. It triples in length, staying on its line. Red eigenvector v2 sits on the opposite diagonal. A -1 eigenvalue flips its direction along the line. Not every matrix has real eigenvectors. A matrix that performs a 90-degree rotation, for example, knocks every real vector off its path, meaning no real eigenvectors exist for that system. When they do exist, eigenvectors reveal that a complex shear is actually a simple internal system of stretching and flipping along specific axes. If we ignore the standard grid and view the transformation through these diagonal lines, the shearing motion disappears. We see only expansion and contraction. These lines act as the structural skeleton of the transformation, showing us the hidden geometry that defines how the space moves. This math translates directly to the physical world. Just as our matrix has natural directions of stretching, physical objects have natural directions of oscillation. Civil engineers calculate these eigenvectors to find a bridge's vibration modes, the specific ways the structure prefers to sway, allowing them to design against a collapse. In data science, a technique called principal component analysis uses these same calculations. By finding the eigenvectors of a massive dataset, researchers can identify the primary directions of variation, cutting through the noise to find the most important patterns. Finding this mathematical skeleton allows us to predict and control systems that appear overwhelmingly complex by focusing on their few unchanging structural pillars. This logic holds as we move out of a flat plane and into a volumetric space of 3 dimensions. Whether a matrix acts on 2 coordinates, 3 dimensions, or 100 different variables, its instructions will always attempt to twist and mix the data. By isolating the vectors that refuse to turn, we find the universal anchor points that render a chaotic universe computable.